All right, let's go ahead and at least start messing with some code real quick. Let's go into our class code. What do we want? dr binary tree, call it a 1. Oops. Oh, because we did binary search. All right, what do I want to get here? Oh, do I have a template thing here? No, I don't want that. Don't I have insertion of linked list? That sounds great. Okay. All right, we'll go into the src directory. RM. Okay, so let's go ahead and gvim source main.cpp. We're not doing a singly linked list. We're going to call it a binary tree.hpp. Yeah. So how do we want this binary tree to behave? Well, we probably want to do a binary. It's actually going to be a binary search tree. We want to go ahead and give it some type, so we'll have it be of integers. I'll just call it the BT for B tree, binary tree, or BST. There we go. All right, what do we want to be able to do here? We want to be able to add. Add. All right, what's some values? You want those up there? Sure, why not? Okay. We have 2, 3, 54, -22, 45, and last one's 1,000. All right, and then probably want to do, what's that? Okay, whatever, magnitudes. Let's see. Print in order. All right. Sound good? Sounds like what we want? All right. Notice how I dictate what we want, and then I'm going to actually make it happen. Let's first see if this compiles. Should be a no. Yep, because we don't have binary tree. That's great. Tab new source binary tree.hpp. If not defined, binary tree underscore HPP. Go ahead and define it, and then end if. All right, so template on class T, make our binary search tree. Private, and then public. Okay, so what's going to be inside this binary search tree? Or just a pointer to the first node, right? We could do that. Yeah, a pointer to the first node. So we need to come up with some type of binary node type T, and we'll call it mhead. Or actually, we'll call it mroot, because we're using trees. Is that actually all we need? I think so. Yeah, pretty much. Oh, great. Yes. Now, we already defined some functions that we want. We wanted to do a void add const t value, and we wanted to also do void print in order. Right? Those were the two functions. Okay. Well, what else do we need to create? We need to create a binary node. All right. Template class T, class binary node. All right, so what's inside of this binary node? Yes?
Why do we bother saying constant if C++ can just cast it to void and modify it anyway?
It's good to at least dictate when a value is not supposed to be changed. You're basically saying in this interface, whatever you pass to me, I'm not going to change it. Okay?
Would you say that's more for the programmer than?
Nowadays, it is more for the programmer. Back in the day, it was definitely a compiler thing that would help the compiler optimize your code. And probably in certain situations that will still work for the compiler, but modern compilers are able to do interfunctional optimizations, aka they're able to decide whether a variable is actually constant or not, and then move from there. Okay, so what's in this node? A value, so we got t mval. Okay, so binary node m left, m right. Okay, let me go and make sure people are on the same track. Here's your node. Value we have stored pictorially as a number inside of it. You have m left. m left and m right, which points to another node, which of course has more pointers to the left and to the right. Okay, all right. So this is OP, and we need to do some encapsulation here. So let's go ahead and do our getters and, well, let's go ahead and make our node first. So let's go ahead and pick our binary node. We want const t val, and we'll do binary node left. Ooh, I didn't spell binary node correctly. Binary node for the left, binary node for the right. And then we're going to want to do our standard getters and setters. So, oh man, all right, no easy way to do this. Void set val, constant t val. Go and spell that correctly. We're going to, of course, be able to get it. And then we're going to need to do the same exact thing for the left and the right. All right, set left binary nodes of t left. Let's go and do the same thing for right. And then we're also going to want to do the standard getters and setters for the get left and get right. Now, did y'all do getters and setters? I hope. What's your question? Yes.
So is that sort of the getters and setters? Is that more so you can interact with what was it, your private variables in main?
So this is the purpose of this is encapsulation, so that if they ever try and get, or if they ever try and set your values, you are able to intercept it and ensure that the value they're sending to you is actually legit, or if you need to change something, it's easier to change code later on because it's always done inside of one function. Yes?
Your set right also has left.
Thank you. All right, so a lot of this work is actually setting up the,
Why is it get left and get right?
because I didn't type it out correctly. How about that?
Yes.
Good call. Any other catches? Nope. All right. So tab new source. Where we got my. Whoop. We do need a destructor. The destructor. Okay. All right. Let's go ahead and. This is when. Wow, I can't type. Template class T. All right, we're gonna. This is the one time when an IDE would be useful. Binary nodes of T. All right, let's go and start spacing this out. Actually. Hey, look at that. All right, great. So for a binary node, if you have the vowels, well, you're just going to set them. M left equals left. And of course, M right equals right. It's very important you actually do all these, but in fact, I did this wrong already. Yep, I did. Get it together, man. Why am I calling these other functions? Right. Yep.
Wait, what's the
So now I'm calling the setters to actually, yeah. All right, I wonder if this compiles. We should. Oh, almost. Undefined reference domain, probably because I never wrote it. All right, so we're almost there. We need to also do this one as well. Hey, look, there's only, well, we probably should have a constructor as well, so binary search tree. And then if we have a constructor, we need a destructor.
Because they have pointers.
Maybe. Yeah, we may want to do that. We'll go, I'll let y'all consider that.
And then include the CPP, don't we?
Yeah, we're gonna have to include the CPP because we're using templates. Yep. Yeah. Would be nice that C++ solved these problems, but they haven't. Whoops. Perfect. All right. Now let's see, it's going to almost work because now we haven't included it, as you pointed out. So we need to include binary, whoops, in quotes, binary tree.cpp because we are using templates. All right, redefinition. That's probably because we're including the CPP one too many times. So, if not defined, what was this? If defined, there we go. And then at the very end, end if. There we go. Hey, look. Oh, we need to fix this make file because it still has a linked list test. So let's call it the BST test. It does nothing. Great. Hey, our code compiles. Okay. We're getting there. So notice there is a lot of overhead to set things up correctly. It is important to do that because if you don't, you're going to run into more trouble later on.
Trouble or success?
What's the difference?
I was going to ask you that, actually.
Yes.
So basically, we're doing more, so later on we have to do less.
Yes. It's like test cases. You write them now so you don't have to mess up later on. I just have done this for a while, so I know when I need to write a test or not. All right, for the constructor of a binary tree, what do we need to do? Well, we're constructing the binary tree, but we haven't added any values. So what's mhead going to point to? No, right. Yeah, we haven't created anything, so mhead or mroot, sorry, equals null. All right, that was good. Constructor, we'll just put a big to-do. Fixed me. All right. So add. All right, so we're going to make a new node. Great. Binary. Did I call it binary node? I think so. Binary node of type T star new node equals new binary node. T, and we're going to pass it in the value, and then we'll go ahead and say the other things are null for now.
Now we need to say if mroot equals null, this is the root.
Okay, so we create the new node, ending my sentences with semicolons. If the root is null, update root and exit. So if mroot equals null, mroot equals new node, and then what do? Return, so we're not doing anything else. Great.
It's not that, it's the left to the right.
Right, so now we need to go left and right. Ooh. Yeah, you can do this either way, recursively or iteratively. You want to do it recursively? We could do a while loop. We could do a rover. We can do it either way, guys. It's actually, I don't know. And for add, I actually don't know which one's easier. I can tell you for printing, the recursive one is way easier. But for add, you can go either way. Anyone? Recursion? We'll do it via vote. Why not? Who wants to do it recursively?
Yeah,
Okay, iteratively. One person. Oh, two. Thanks, Perry, for and three. Okay, so at least we got some people that are naysayers. That's great. So we'll do it recursively. All right, so if you're going to do it recursively, I suggest you do a recursive add. So normally you want to make that a private function because you don't want people outside of your class using that function. So I'm going to call void just add recursive, and you simply just have a binary tree node. Thank you. I'll call it node, and then binary node, new node. All right. Could have called it other things. I called it this. Let's go ahead and get this guy in here. So we are basically going to then say add recursive on mroot and passing in the new node we just created. Perfect. All right. You're in add recursive. What's the first thing? It's a recursive call. What is the first thing you do? All right. Find what the base case is. This is actually just a bunch of base cases and then calling itself again. So now, luckily, this is a private call. So what we can do is private call, and this is very common, precondition node is not null. We know that because we just passed in mroot, and we just did check if mroot is null. And since it's a private function, you are allowed to make certain assumptions because you know how you're going to use it. But I highly recommend you put those assumptions as a comment up before the function, so when you go and you try and figure out why your code's not working, hey look, you at least made a comment about it. So we don't need to check if node is null. We know node is not null. So what do we do?
Do we compare the value in the node with the new node?
Right, so if node.getVal is less than new node getVal, what do we do?
We check the get left as well.
All right, so now if node.getLeft is equal to null, if it is null, what do we do?
We set the new node.
All right, so we just go node set left equal to the new node, and then you return. Very important. Otherwise, what are we doing?
Set the node. I will call the function.
Yep.
Left.
Passing in node get left and the new node. All right, hold on. I got a couple of confusing looks here.
Wouldn't you have to move the one node before you actually left?
Hold on. First, check if the value is less. And I may have done this wrong. If the current value is, actually we want it this way. Because if the current node you're on, like if you're adding the 5 over here, you're adding the 5 and you have the 2, if 5 is greater than 2, then you want to go to the left. So it's good that we wrote the diagram out. See why writing the diagram is a good thing. So now we can see when we have a couple of errors with our math. Yes?
Okay, so I wanted to ask this question about the binary search tree. What if we have like two values which have the same value? How do we go?
So that is going to talk about between a set and a list. It depends on how you wish to do it, but you want to order it such that it's either to the left or to the right. If they're equal, it's always going to the left. That way you're saying everything to the left is strictly less than or equal to it. So as long as you have that ordering less than or equal, it's in there. Of course, we're applying that here with greater than, because if it's equal, then it's not greater than, so it's going to actually go to the left as well.
So usually it's like to the left.
It depends on how you want to set it up. It actually does not matter because if you go left or right, because it's still a binary search tree. But you do have to be consistent within your tree. That's all. Good question. So first check if the value is less. If we have an open spot, fill it and exit, because that means we found where it is, because we start at the 5. Initially 5 had nothing. And then to the left, so you went to the left and it was a 2. Well, I'm sorry, you went to the left and it was null, so you just put that node right there. Let's go ahead and draw that pictorially. So we added the 5. We already did that code. If mroot is null, you just make that node. Everything points to null, and you're good to go, right? Everyone tracking? Yes, OK. Now we have this new node equals 2, pointing, of course, to nulls. So we start at 2. We start at 5. We start a recursive call. Is 5 greater than 2? Yes. So we go into this if it's greater than 2. Then we ask, well, is 5's left null? Is it null? Yeah. So then we're going to move this 2 over here. I'll draw a tutorial. A new node is still pointing to that. But we're done, so we're going to exit. Now, if there was something on the left, aka it was not null, then we need to go ahead and do the recursive call again, checking the left. All right. Now, if the value is greater than or equal, notice I don't have to do an if check because I already did the first check up top, so the code right here is going to be the exit value. So now we just first, if we have an open spot, fill it and exit. So if node dash get right, yeah, right, equals null, set, which one? Right, equal to the new node. Let me spell new correctly. And then return. Otherwise, what are we doing? Yeah, add recursive get right new node. Are we done?
How come when you have something smaller, how come you have to move the bigger one like over one end of the list?
I'm sorry, say that again?
So like if you have like, if the first position's 5 in the ASL, if you have one less than, I wouldn't have to move down 5 to the extra space.
Oh, because you're actually updating the pointers. You create the 2 and then you fix the pointer so it's going in there. And an array is where you have to move, shift things around. Linked list, you're just fixing pointers. Binary search tree, again, with this implementation, we're using pointers. We'll talk about later how to implement a binary search tree with an array, but don't worry about that right now. We're going to do it with pointers. So yeah, with this, so great question. Did I answer it? Okay, good. Any other questions? Are we done? Looks good. Let's see if it compiles and does not go in segfault. Hey, it didn't segfault. That's great. But we can't really test it because we have no way to search it, right? Or print it out. So we need to print. Okay, print in order. All right. This is going to be way easier recursively. Way, way easier. Yeah, so we're going to do, no, well, sure. We'll, no, we have get val, so we should be good. Print in order recursive. Binary node sub t start node. All right, so a lot of times with the recursive calls that are being implemented inside of a class, the main function simply calls a recursive call and just sets it up. So for example here, binary search tree sub t print in order. Here we simply call print in order recursive, passing in mroot, because obviously we want to start at the root. Okay, So, let me help you out here. You want to traverse the whole thing? Yes.
Shouldn't we first make sure that invert is not null?
It doesn't really matter because we're doing this node, this print in order. So what's the base case for print?
It is null, then we don't have to do anything.
All right, if node. Sometimes it's easier to just do it here. If we want to set this up, I'm going to help you out. Print in order recursive node get left. So it goes down the left side first, and then it goes down the right side next. All right. Right. So in between we print them. Yeah. All right. So let's see. We'll just have a space. Okay, let me go ahead and include stdio. IO stream. Another thing we probably want to do is put in a \n once we're done. All right, so how's this?
You have to keep checking the left. I don't see this null. How you?
Well, we already did that with our if node equals null up top. Anything else we need to do?
It doesn't look like we're like moving down more than like one.
Well, we're calling ourselves here, so we keep calling ourselves down the left way each time. Let me go back over here and fill out this binary tree just to show you what the code's doing. Binary search tree. All right, so we got a 3 over here. We got 54 right here. Negative 22. 45. And of course, 1,000. Okay. Hey, looking nice, Claire. So we started 5, right? We're going to, because that's what mroot is. Mroot points to 5. Everyone with me? Okay. So we're going to call print in order recursive mroot. So we're going to start up here with mroot. Is mroot null? No. You did this. No. It's like getting mixed messages. So do we print the node? No, we first go to the left. So we're going to go to the left and call print recursive. And I'll go ahead and I'm going to print in order recursive call. It's going to take me forever to type all that out, so I'm just going to call it PIR on 5. So next call is PIR on 2, right? And he's not null, so we're going to go to the left again. Did y'all see that? We started with the 5, from print recursive on 5 up to this node, so we started up here. We're on that call. We need to go to the left. We're still inside that call, but we're calling ourselves again with the 2. So we're inside of print recursive, in order recursive 2. We're at this guy. He's not null. We're going to first go to the left, which is negative 22. Okay? 22. We're going to also go to his left next, which is what? Null. Since he's null, what do? Return. So we get rid of him. Now with the negative 22, we have just finished this call. We're going to print. We're going to do what? Print it. So I'm going to go ahead and, right here. 22, boom. Now what do? We go to the right. Passing in null. And if you're confused why we're going to the right, remember we just called this, so we're going to go to the right. The right is null, so of course we're going to return from here, go back to the negative 22, and that's after this function call, so what do we do here? We go back up to the 2. Now where are we in the function call from print in order recursive 2? We just finished calling which one? The left. We just finished calling the left. So what do we do next? We print it. Then what do we do? Whoops. We go to the right, which is a 3. When you're at that 3, 3 is not null, we immediately go to the left. Left is null, we pop back, then what do? We print it. And then we do what? Go to the right. That's null, so we're going to return from the return from the right, and then what happens in the 3? We return it. We return because we're at the end of the function. We go back to the 2, and what do? Return because we're at the end of the 2. Go back to the 5. We're returning from the left, so what do? We print the 5. Then what? Go to the right. So. Then what? We're at the 54, so go to the left. We're at the 45, what do? Go to the left, right. That's null, so we're going to return. All right, here's the question. What data structure is this? What data structure is this? It could be implemented with a singly linked list. It's not a core data structure. What is it? What are you always adding to? Are you adding to the top? Adding to the bottom. What are you removing from? The bottom. So you're adding to the bottom and removing from the bottom one at a time. Which data structure is that? It's a stack. This is a stack, guys. When you, so, come on, loud and proud. Second, yes. When you do recursion, you are using the implicit stack of the computer. Okay? And where else have you heard the word stack? Stack memory. Stack over. It's all the same thing, guys. The stack from memory is utilizing the stack of the data structure, which is inside of memory, which is just a stack as you're adding and appending and removing. Right? Okay. Everyone got it together now? All right. So this is just a stack. So we just came from the left side of 45. So we popped off the null. I'm going to start saying those terms. What do we do next? We print the 45, correct? And then we go to the right, which implicitly pushes print in order recursive null onto the internal stack memory of the computer. That's null, so what do? We return from it, aka we pop it. We're at the 45. What do? We return from it, aka we pop it. We're at the 54. What do? We print it. Then what? Recurse going to the right, which allocates print in order recursive function call on the stack, or allocates it on the stack, which is just like your stack data structure. Then what do? We go to the left, so we allocate the same function call with null. Now what happens? We return, so we pop that function call off the stack. And then what? Hold on. We just returned from the left side of 1,000, so we're going to print 1,000. Then what do? We go to the right, thereby allocating another function call on the stack. He's null, so what do? We return, aka pop. We're at the 1,000, what do? We pop, or deallocate. We're at the 54, what do? Pop, deallocate. This is all the same thing, guys. It's all the same thing. We're at the 5. What do we do? Pop, deallocate, pop. You got it. Yes.
How do we know once you've already visited one? So, like, if we go up to a 2 back from like,
Because the stack, the implicit stack of the memory system of your computer is keeping track of where you are.
wouldn't we have to check that or see if we already had it?
No, the computer's handling that for you. You see how I was writing these out like a stack? Because you call here, it calls another, to itself calls another. Each time you call yourself, you're allocating memory for that function on the stack, and then you can pop it later. All right. Okay, guys, so when you're doing recursion, what data structure are you utilizing? Okay, good. That's a great give me midterm question. Thank you. I will add that one. That's a good give me. I like doing a couple of good give me's on the midterm, guys, because I know how this course is. What's another good give me? I will ask you this.
What is a pointer?
What's a pointer? Okay, that's not quite a give me, but yes, what is a pointer? That one's a little tricky. I will love to ask you what is the best data structure. You only need 2 words.
It depends. Please make that question.
It is gonna be a question.
I usually ask that.
With one option.
What option that you can select from?
Because I think everyone will remember it for sure.
That's good. Yes.
The answer is actually bubble sort.
Bubble sort? No, that's not even data structure. Oh, that was good. Okay. All right. Let's go ahead and pause the video.